I will show you some simulations now, which will also help you understand these questions that we just discussed, and then take up rest of the questions later. Let's see. Can you see my MATLAB screen?
Yes, sir.
Yes, sir.
The figure as well? Can you see the figure?
No, the figure we cannot see.
No, sir.
Okay, let's see. How do I? Can you see the figure now?
Yes, sir. We can see.
Yes, sir.
Yes, sir.
Okay, perfect. Okay, let me run it again. So what we're gonna see here is let's see. I believe you can see my presentation as well, right?
Yes, sir.
Perfect. So I'm going to show you a simulation of a particular industrial relevant scenario, right? There is something called choke plugging. As we have discussed earlier, we have the drill cuttings that are transported up the annulus, and we have a choke at the surface, right? Sometimes for various reasons, right? So if you have a particular type of drill bit that's creating different type of rock cutting, or if your drill mud is not engineered properly, or because of some the reservoir properties where it just has flakes, etc., you may have caving. These small cuttings and etc. can go and plug the choke at the surface, because it is a small opening that's going through at the surface. And what happens is, if there is an accumulation of these cuttings, then it will start to choke, it will start to plug the choke, and that's what we are trying to simulate here. And this particular scenario is really important in the managed pressure drilling applications, because you have two chokes usually run in parallel in the field setup. So if in case one choke is being plugged, then you always want to your controller or the automation system should understand that, yeah, okay, this choke is getting plugged, now I have to close this and then deviate the flow through the parallel choke, right? So we need to understand how the dynamics are going to occur in that kind of situation. How we simulate that is, we have the choke opening that is given by ZC, which is an input, as I've shown you earlier. So what we do at 1 minute is we suddenly set it to 0 with a particular ramp, which means there is a plugging of choke, and then it's completely blocked. The fluid cannot flow out. But you cannot know this immediately, because you're constantly pumping the fluid on the other side and your pressure is increasing. But first I'm going to show you the simulation for that particular situation. And you can see how that pressure increase from the choke travels down the annulus and also goes up the drill string and then keeps reflecting. So watch out. Red line denotes the pressure profile in the annulus side, and blue is on the drill string. So you have a pressure, and then you have the pressure drop, that is the drill bit, and then here is the pump pressure. So you close the choke, that creates a pressure wave, and then this pressure wave is traveling down. It will go to the annulus, travel through the bit, and then travel back up to the drill string as well. You can see that the pressure wave reflects in the annulus and also travels up in the drill string. So what happens is, when you keep your flow constant and your choke is plugged, you will have multiple wave reflections of this sort. And every time, if you notice, the pressure profile is moving on the right hand side, which means you're constantly increasing your bottom wall pressure. because of the reflections. So at some point, if you don't identify that this particular scenario is happening, you might go to a pressure that is higher than your fracture pressure, and you might as well fracture the reservoir, right? So these are some of the safety critical situations that we have to encounter. Of course, it is a contingency, but we need to be prepared for that, right? So let me stop that and okay. Can you still see my screen now, the presentation?
Yes, sir.
Perfect. So here is the simulation, or it's an example of the same simulation, right? You close your choke, and then your pressure will increase suddenly at the choke side, but that particular wave takes some time to travel down the wellbore. So this peak travels and reaches the bottom of the wellbore. PDH is your downhole pressure, right? So you affect the monomal pressure after a particular time, and this difference is the time taken for the pressure wave to travel down, and it travels at the speed of sound in that particular medium. And once you don't do anything else and you keep the choke plugged, this wave is again going to reflect at the top and then back and forth. And you see, within a few minutes, your bottom pressure can go up to 60 bars or higher, right? And generally, our drilling window is quite narrow, and we don't have 60 bars to play with. We might only have 5 bars or less than that, or up to 10 bars to play around, right? And it is getting increasingly narrower. So if you consider a pressure window of 5 bar, that's a very tight pressure control that you need. And if you don't have that, then you will fracture your reservoir. Once you fracture your reservoir, you're losing your fluid. If you lose your fluid, you're losing your hydrostatic head, which means you're going to decrease your bottom wall pressure, and it's an unstable feedback loop, which you don't want to have. So how do we achieve this particular simulation is by using this particular model, right? So this is the distributed dynamics of the fluid flow in a single one-dimensional pipe, that is given by Euler's equation. The first equation is your mass balance. Here, if you remember from the ODE system, we considered density to be constant throughout the whole control volume, but that is not the case in the distributed, because you want to see how these pressure is changing and how this liquid is being compressed because of the varying pressure that's coming or traveling through the wellbore. So all the terms are function of both time and the location. And here is your mass accumulation, and here is the difference between the flow. Same goes to a momentum balance equation. It's the same formulation as we had earlier, but just that instead of reducing into an ODE or a simplified model, I'm showing you the distributed dynamics. So here you can see it as some kind of the kinetic energy that has some potential energy from pressure. You have the mass accumulation or the momentum acceleration of the fluid. You have the source terms that is given by friction and gravity. The reason why I have plus minus is if you remember again, in your drill string, you have gravity that helps your flow, right? Gravity helps your fluid flow since the fluid is traveling downwards. If you need to model the drill string, you use positive source term, and in case of annulus, your gravity is acting against your fluid flow, and that will reduce your acceleration. It's a loss, so you will use a negative sign. But friction is always going to act against your direction of fluid flow, so you will always have a negative source term or a pressure loss out of friction, both for drill string and annulus. So since it is an introduction to modeling, I'm not going to concentrate on how to solve such systems or how to combine drill string and annulus and reservoir using a distributed model, etc. So we will not look into how to solve it, but the main goal was to show you this particular simulation of why we need distributed dynamics. And the same goes for another industrial specific scenario, which is connections. So whenever you drill or you are tripping out, connection is a process that is repeated several times when you drill for a wellbore, right? What exactly is connection is you stop let's assume that you're currently drilling, your pump is active, fluid is flowing. What you want to do is you stop your pump, you bring your flow to zero, disconnect or connect your pipe, add or remove the pipe, and then you start your pump and you increase your flow slowly so that you reach to the bottom hole pressure again, right? And you can continue drilling. This is the connection process. This is a sequence, and that's exactly what is shown here. But we are trying to do that in the MPD setting. Let us say we are managing the choke manually, right? This you cannot avoid. You're gonna reduce the pump flow. JP is the mass flow rate at the pump. You're reducing it, bring it down to zero, right? Because you're gonna connect or disconnect it. So you cannot have any flow at all. And during this time, if you want to compensate for the frictional losses at the bottom hole pressure, if you are having a tighter pressure window, then you can compensate it by closing your choke, so your bottom hole pressure increases, right? Now, when you have these two control at the surface, you can see what's going to happen in the bottom hole pressure in the bottom of wellbore. Since we are doing it manually, we might excite the system, and you can see this wave reflections. We may have some of this dynamics that is happening during this connection process, and you increase the bottom hole pressure to a higher value than required. This is possible, and or maybe lower in some cases, and that is what leads to connection gas or influx during connections, or even some fluid loss during connections. These are the reasons for that, because when we operate it manually, you don't know how the dynamics are excited in the system and how that in turn affects your bottom hole pressure. You can see here the choke pressure because of your choke closure. You can see that it is still a ramp, which means you are closing the choke at a particular rate. Even then, that still excites your systems and you have wave reflections. Okay, so what can we do? So the area that we are focusing on is towards automation, right? You want to tell a controller or design a controller that can automatically maintain a particular bottom hole pressure for you. You don't have to do it manually, right? Now, what you say is, I'm going to compare this. This is a simulation results from my PhD work, and it was also published. I have the reference later. I'm going to explain you the connection scenario using two different models. Design model here is the ODE model, right? And the simulation model is your distributed model that I have shown you. PDH is your bottom hole pressure, ZC is your choke opening, and PC is your choke pressure, right? So what I'm saying is, dear controller, I wanted to maintain my pressure at a particular value given by this dotted red line. So operate my choke in such a way that I can just stay in that line, right? So what the controller does is, okay, now you have the reference signal. This is what I have to maintain. And the controller says, okay, if I have to maintain this particular pressure, then I need to change my choke pressure in such way. Because you already have given the controller already knows what is the type of ramp that you're gonna implement for your pump, right? You know how fast you're gonna reduce your flow from a particular value to zero and everything. That is all given. So from that, and using the ODE model, the controller calculates, okay, if I have to maintain this, I'm going to maintain such pressure at the choke side. And then it also calculates, if I have to maintain this particular pressure, I need to change my choke opening accordingly, right? So that's what it does. It wants to track the pressure and it accordingly tries to change the choke pressure, the choke opening. And you can see at some points, the pressure drops and it cannot maintain at the particular value. But it's definitely much better than a manual operation. And I'm sure you'll have a lot of questions about why do you have this spike or overshoots? Can we avoid this? Yes, we can. If you tune your controller in a particular way and account for the dynamics and the actuation. So this is the price that you pay for approximating certain dynamics, right? Even so, you can still see that the pressure and everything is very smooth and the controller is able to track the choke pressure very well. But on the contrary, if you take the simulation model that has this distributed dynamics, you can see that in order to maintain a particular value, you know that the simulation model, in reality, you have this pressure wave propagation as soon as you try changing your choke opening rapidly. And that excites your system. You will see this pressure transients, and you see that the controller is struggling to maintain this particular value. It's rapidly changing up and down, closing and opening to see, okay, I have to stop somewhere and come closer to this particular value. So this is the clear difference between two different models in terms of designing a controller or an automation system. Because your controller will be, your controller cannot maintain the required dynamics, and you cannot compensate for the dynamics if you don't include that in your model. So if your model itself doesn't account for such dynamics, then the controller cannot see it. So it is important to have a nice model and that can also account for the distributed dynamics. So then you can instruct your controller to go and maintain that particular pressure. So here is an example of a proper industrial application of automation and why we need good modeling, right? So, right. So I will stop here for now for more questions, if you have any. Do you have any questions? Okay, so let me just go for the last part of it. So I'm just showing you again the ODE model that we derived. Now you have, I am think through the presentation. Now you have an understanding of the model for wellbore. That is the fluid dynamics that occurs inside the wellbore, drill string and analysis. But we also need to consider an important dynamics from the reservoir. So that's coming in from QRS, right? So there are multiple ways to include that particular dynamics. If you have already started learning reservoir engineering, you must be aware of these two particular type of solutions, which is the influx is given by CTRS. That's nothing but the constant terminal rate solution. It's an approximate representation of your influx um, for the transient states. And later, when you produce a reservoir for a longer period of time, you can approximate it using a quasi-steady state equation, famously known as the productivity index type relation. That's PI type, right? So PI and the eta are different proportionality constants shown here. But so again, this is an approximate solution. This is equivalent to having an ODE for wellbore dynamics. This doesn't have any dynamics at all. As you can see, it's static relation, but one that is dependent on time, one that is not dependent on time. here it's just depends on the drawdown, which is nothing but your difference between your bottom hole pressure and PE, which is the reservoir pressure at an infinite extent. And I will shortly show you where this particular pressure is. And this proportionality constant is function of all the reservoir parameters like kappa, permeability. H is the thickness of reservoir. RW is the radius of wellbore. Mu viscosity of the fluid. C the compressibility. Phi the porosity. Gamma is a proportional. It's a constant. And S here is the skin factor. It can be positive or negative depending on how much, whether we stimulate the wellbore or if we have more mud cake or sand productions or pressure. It's just an additional factor for the pressure loss. And we can consider that it as zero during the real-time operation when you want to model real-time drilling operations, because when you just drill your wellbore, the reservoir, the formation is very fresh, and it will not affect your skin factor at all. With prolonged production, or if you stop your drilling activity for a very long time, then you will slowly have the buildup of mud cake, at which case you might have some additional skin factor. So if you want to go towards more accurate model for reservoir influx, and that is given by the Darcy's law, I believe that you are already aware of this particular relation as well, which is dependent on the near wellbore pressure gradient, that is P at RW, dPdr at RW. Where does this RW and RE lie, right? So that's given by, so it's the gradient at this particular wellbore reservoir boundary at RW. RE is the reservoir extent that you're modeling, generally 100 meters or 200 meters, whichever you think as the right extent at which your pressure is not affected. Which means if you change the pressure at this side, it will slowly transport on the other side, and you will not receive it until maybe a few days or few months, right? So that's the point where you have to consider your RE, and PE is the pressure at this particular extent. Since it's the gradient of pressure at the near wellbore reservoir boundary, you need to first understand what your pressure distribution is. And P here is your pressure distribution of the reservoir fluids inside this radial section. So that's why it's a function of T and R. R is the radius, and that's a function of some derivatives, double derivatives. This is called as the diffusivity equation. And epsilon here is a function of your reservoir properties, and epsilon is known as the diffusion constant. So it depends on the reservoir that how fast or slow your pressure gradient is going to transfer into your reservoir zone. And we need to, when you need to solve certain model, you need to always have a boundary condition, like we need to have boundary conditions on either side and also have some initial conditions. Boundary condition that we have here is that the reservoir pressure at RW is exactly equal to the bottom hole pressure, right? It is a valid assumption or valid relation, because as I said, as you drill immediately, you're gonna have immediate mechanical equilibrium between the wellbore and the reservoir. So you have the pressure that are equal. And at the reservoir extent, infinite extent of the reservoir, you set the flux to be zero. This is the valid assumption when you have a native reservoir and you don't have any other well, let's put it in a different way. If you're having an injector on the other side, and if you want to maintain the pressure at this particular extent, and if you keep pushing the fluid, then you will maintain a particular pressure. So PTRE will be a particular pressure PE, since you want to maintain a constant pressure. But here in the transient setting, you're saying that the flux is going to travel all the way along. So it's a zero flux condition on the other side. So I think I will stop here, because I have some derivations for the reservoir fluid model, but can somebody from the organizing team come out on mute and let me know how we are on timing and what we want to do further?
Yes, sir, you can carry on.
Okay. What about the audience? You guys are feeling bored or should I continue?
No, sir, you can continue, sir.
Okay, maybe I'll be really quick in showing you how to do that. So here is the model, and yeah, so we have the Darcy's law, which is going to give us the influx rate. We will again use the first principle methods, by which I mean we will apply the mass conservation for this particular radial section. You can see that the fluid is coming in from the right hand side and then coming out through the left hand side. And if you apply mass conservation over the small section dr, this is the fluid that is accumulating in the dr section, and that's given by the mass flow. Sorry, this is the mass accumulation in the small section, and this is given by the gradient or the flux between in and out values. You can see here on the right, it's a function of porosity and density, but it's a derivative with respect to time. So we need a special treatment on how to modify this term so that we can establish it in terms of pressure. Now this particular derivative can be converted into differential equation and pressure, but we again need how the porosity and density inside the reservoir is a function of how it varies as a function of pressure. Apply chain rule, then you will have two different terms. Take your porosity and density out. This gives you, let me show. Okay, this is actually a term for compressibility. So density relates to the compressibility of the fluid, and this particular term in porosity gives the compressibility of the rock. So you can see that it takes into account how your porosity is going to vary with your pressure. Adding these two, you have a particular term that's the total compressibility of the reservoir fluid system. And voila, you have the term and you have the pressure term in time, right? You substitute that in the previous equation, you get such terms, and you have only the diffusion equation with respect to pressure, both radially and also in the time domain. Same boundary conditions as I discussed earlier. And in a simpler form, you come down to this diffusion equation, where your diffusivity constant is given by different reservoir properties. Well, mainly porosity and permeability, right? Okay, that was quick anyway. Here are the used references for this particular talk. So, as I said, Glenn Koza is the author of this particular paper, which was the ODE model that I presented earlier. He's also the CEO of Kelda, and I had a pleasure of working with him for quite some time. I took his model and then modified it and provided an extension to COSA model so we can include both the reservoir dynamics and the pressure loss across drill bit. And I have another paper that we published with my colleagues, which studies the controller performance for managed pressure drilling systems, and the simulation result that I showed you that has an automatic controller to maintain a bottom wall pressure during connection scenario is a result of this particular paper. And if you need to know more about how to couple the influx model, the distributed model for reservoir, into a distributed model for wellbore, you can refer my paper here that has detail of yeah, it has a comprehensive detail of how to model the systems. And if you want to learn more about how to couple the ODE or the COSA model with the distributed pressure system for reservoir, then you can refer to my paper that was published on 2019. So in the same conference in 2019. And you can also look into my PhD thesis, which will be available online soon, where I detail how to modify these particular models to include um, different types of dynamics. So I would like to conclude this talk that what I will just give you a summary of what we have seen. We have seen the derivation of the simplified COSA model. I also have learned about how to extend it to include different types of reservoir influx. We have seen how the lumped and distributed dynamics are a key factor in simulating industrial scenarios, for example, choke plugging and connections, and why we need the distributed models for designing a controller or your automation systems, right? And we briefly touched upon the distributed models for both wellbore and reservoir, just the format, just to give you a sense of how it looks like. And yeah, so if you want to know more about how to solve such systems or how to solve the distributed system further, or if you like this particular topic, then of course I'm more than willing to give you another webinar or a series of classes to give you a hands-on experience of how to solve the systems, which is possible. And thanks for your attention, and thanks again for FIPI and Nahil in particular to organizing this. And you can reach me out in this particular email ID. You can check out my website. I will try to update and keep it live and update you with new things that are happening. So now you can ask me any questions if you want, if you have any.
Sir, I have a question. Like,
sure.
Is it possible to implement this automation on the fracture reservoir?
Automation on the fracture reservoir. So when you say fracture reservoir, what it means is you're only worried about your pressure profile, right? So you in your fracture reservoir, you have the pressure that is too less, right? So you can always have a tighter control if you can include the fractures in your reservoir and put a, how should I say it? In simple words, it is possible, but you will never drill into a fracture reservoir. And that's exactly what you want to avoid most of the times, right? So I wouldn't see, even if you want to drill through a fracture reservoir, you can dynamically manage it through MPD systems. And yeah, you don't need to have a fractured reservoir model to do that, because even in the same reservoir model, you can fix your pressure too low and tell your controller, okay, don't go above this. So you have to be less than that, right?
Thank you,
Does
sir.
that answer?
Participants, do we have any further doubts? Okay, thank you participants for your patience. Now, I would like to express my sincere gratitude to Dr. Navin Velmurugan. As I have already given an introduction to Dr. Navin Velmurugan, but I want to let you know that he is an IWCF certified professional with almost a decade of academic training in E&P segment. Thank you very much, sir, for sharing your cognizance with us. It was a wonderful session. Thank you for sparing time for this. We hope you liked this experience and hope for you to join FIPI PDPU in other such events as well. Thank you, sir.
Definitely. Thank you so much. And thanks for organizing it pretty well. I really enjoyed it. And please feel free to reach out if you have good interest from the participants to know, to learn more, then I can actually can definitely come on and give you more classes, more detailed into particular ideas. So yeah, thank you so much for the organization, and stay safe. Take care. Cheers.
Thank you so much, sir. Thank you, sir. Thank you, sir. Participants, you may leave now.
Okay, thank you.
Stop the recording. Recording stop.